uh, resonation. So for this lecture, we have with us Dr. Amol Morankar sir. There is a currently assistant professor in Department of Electronics Telecommunication, Cummins College, Nagpur. On behalf of Maharishi Karve Stri Shikshan Samstha and the Mechanical Department and the FDP team, I welcome you, sir, for this faculty development program. Let me take privilege to introduce sir. Sir is basically PhD in VLSI technology from VNIT Nagpur. Sir has completed executive business accelerator program for the College University in New York. Then sir has 16 years of industry experience and 7 years of academic experience. Sir is expert in micro electromechanical system and its semiconductor fabrication with publication. The area on which sir has published many papers, which are Scopus Index, SCI, CSI journals. Also, he has 2 book chapters to his name. So, on behalf of the faculty development program team and the mechanical department and Cummins College, I welcome you, sir. And without wasting time, I will hand over to you. And I request you please start with this session.
तुम्ही करून ना.
Yes.
Good afternoon, all the participants and faculty members, engineers from different organizations. So I am Dr. Amol Morankar, and I will be speaking about semiconductor-based fabrication of dual frequency MEMS resonators and the materials that we have used in the fabrication of this MEMS resonator. And I will talk about this particular topic as we have also a patent granted on this particular design. And as Ashwin sir was talking about the upcoming applications which are based on micro and nano materials as well as electronic mechanical systems. So in continuation to that, I would like to present this MEMS resonator. So as all of you know that MEMS stands for micro electromechanical system, which is a combination of mechanical system as well as an electronic circuitry. So in this particular topic, so in this case, I will just talk about the introduction of the MEMS resonator and design that we have, experimental results, and finally I will conclude on this MEMS resonator. So just I will introduce you, as you know all of that, the Internet of Things has now revolutionized the entire world. And we are talking about different multi-band wireless communication systems. Now, when we talk about multi-band wireless communication systems, we say we have Wi-Fi connections which are based on 2.4 gigahertz, which is based on 5 gigahertz. So we call these as a multi-band wireless communication system where the protocol is same. Only the transfer frequency, which is 2.4 gigahertz or 5.2 gigahertz. But when we say about Wi-Fi and when we talk about Bluetooth, the protocols are different. The applications of wireless communication systems are different. So when we want to combine, let us say Bluetooth technology along with Wi-Fi, then we call it as a multi-standard. So the standards are different and bands are also different. Now, in this particular case, what happens is if we are using conventional electronic systems, which are let's say we have a filters which are tuned at 2.4 gigahertz and 5 gigahertz, then we need a separate filters for 2.4 gigahertz as well as 5.2 gigahertz, because tuning a particular circuit for 2.4 gigahertz and then into 5 gigahertz is very difficult. So therefore, you can see in the block diagram that if we have a three band system or a three multi-standard system, then we need three different filters to filter out the signals which are transmitted as well as which are received. So the logic is to replace these three filters. You can see these three filters which are at the receiver and the transmitter level. So we want to replace these three filters with a single resonating device, which we call it as a MEMS resonator. So that's the idea behind using this MEMS resonator in the wireless communication system. So now, traditionally, what they are doing is they are using discrete off-chip components, which are quartz crystal, surface acoustic wave devices, and bulk acoustic wave resonators, etc. Now, these particular SAW and BAW resonator filters have certain advantages as compared to other filters. So the biggest advantage is the quality factor Q. So they have a very high Q that helps them to select a very specific band of signal and reduce the noise. As well as they also have a very good wide tuning range. But here, when I talk about wide tuning range, I want to really specify that we are not able to tune it from 2.4 gigahertz to 5 gigahertz. It's a too big range. But if I want to tune it to, let's say, when I talk about FM communication, FM, you have been listening to FM radios. So in FM communication, the frequencies are between 90 megahertz to 105 megahertz. So here tuning is possible, but tuning from 2.4 gigahertz to 5 gigahertz is really very difficult. Third point is the thermal dependency. So these particular filters, SAW and BAW filters, really work well from different temperature ranges. So let's say from 0 degree to 50 degree or up to 100 degree. These particular BAW filters also have a good aging stability and they have a very low resistance. So whenever a signal is passed through the SAW and BAW filters, then the resistance or the attenuation of the signal is not very large. But at the same time, when we are talking about the advantages of SAW and BAW filters, let us look at the disadvantages of the SAW and BAW resonators filters. So these resonator filters are fabricated using ultra fine machining technology, which is a mechanical based technology, and the size of the SAW and BAW filters are very big. So those who are from electronics, they must have seen the L plates which were available in the radios some 10-15 years back, and the size of the SAW and BAW resonator filter was really very large. So importantly, what is happening is that now these particular resonator filters has to be connected to the electronic circuitry on the printed circuit boards. So we have to use PCB for connecting all these electronic components along with the circuits. So this particular becomes an off-chip component, and the integration, or we can say portability, the small size of the uh, complete communication system is a problem. So we don't get a smaller size component, smaller size PCBs. So consequently, what is happening is these are off-chip components and therefore they need to be miniaturized. Now this SAW and BAW filter, miniaturization of the SAW and BAW filters is really very difficult. So nothing is impossible, but it's really very difficult. But therefore, now if we want to replace this with our MEMS resonator, so what advantage we will get is, now these particular SAW and BAW filters which are used here, we need an additional amplification stage to amplify the signals. Therefore, there is also an increase in power dissipation of the entire circuit. So when we now why we talk about power dissipation is because these wireless communication systems are mostly battery operated, and therefore the life of the battery in terms of the power of the battery, the discharge of the battery is very important. So the more time the battery remains charged and doesn't require another charging is very important. So therefore we talk about power dissipation. So these are some of the disadvantages of SAW and BAW filters. And now we are looking about, can we replace these mechanical SAW and BAW filters with something which can be placed on chip. So the solution to this particular problem is we can get it through micro electromechanical systems. And what we call this mechanical system is a collection of microsensors and actuators. Now, these particular microsensors can sense different parameters from the environment, and then they have the ability to react to that parameters or take certain action based on the application. So on a particular chip, on a silicon chip, you can have the sensors as well as an electronic circuitry which can act to the sensors and take a particular decision. So you have a miniaturized mechanical system which is electronically controlled on chip. So it is a micro scale system. So the miniaturization is possible because the entire thing can be fabricated on the semiconductor, which the dimensions of the particular sensors, the dimensions of the electronic circuit will be at a micro scale level. Now the advantage of this is, not only it is miniaturized, it requires less power dissipation, but you can go for batch processing. You can manufacture n number of these particular MEMS devices on the semiconductor at a one point. So this like we manufacture integrated circuits in electronics, we manufacture processors in bulk. So the same bulk fabrication process can be introduced. Now these mechanical systems like resonators can be integrated with electronics. So the most biggest advantage is can be integrated with transistors, can be integrated with processors, can be integrated with any other electronic system. So it becomes a complete electromechanical system. So now with reference to MEMS resonator, so what we are what we will be taking here is a mechanical resonating component. So this mechanical resonating component we will use of different shapes, materials, and we will use modes of vibrations to select a particular frequency band. So now if you look at this particular device, in this case, we have four clam beams. Now you can see in yellow color, we have a four clam beams, CC beam 1, 2, 3, and 4. Now these beams are anchored at a particular point in this, which we call it as a clam beam, and these particular clamp beams are then coupled using mechanical couplers. You can see here mechanical couplers which are in the black color portion, and there is a specific reason why we have done this mechanical coupling in this fashion. In the below this, you can see an input electrode which is in the green color, and there are two output electrodes which are in the blue color. Now, this specific arrangement has been done, which we call it as a coupled electrical and mechanical structure, where the mechanical coupling is done through the coupled beams, which are in black colors, and electrical coupling is done using the two electrodes, which are in this color blue, electrode 1 and electrode 2, while the input signal is applied through the input electrode, which is in the green color. Now, the size of this particular structure is in micro dimensions. The total length of the each beam is this CC beam is almost 80 micrometer, and the thickness of this beam is 8 micrometer. So the complete this particular assembly is done within 1 mm square, within 1 mm square. So we call this as a coupled electrical and mechanical coupling scheme. So now what we are going to do in this case is, so let us look at the structure again. So we know with these particular dimensions, we can find out the resonant frequency of this particular beam. And as we talk about harmonics in electrical signals, same, there are different modes of vibration of this CC beam. So in mechanical, we call these as a mode 1, mode 2, mode 3 vibrations. Now, what happens whenever the input electrical signal is applied to these arrangement, and if the input electrical signal frequency matches with the vibration frequency of this CC beam, then this CC beam will vibrate. Right? Now, this particular CC beam will vibrate in mode 1, it will vibrate in mode 2, it will vibrate in mode 3, and so on. Now, this particular coupling arrangement is made in such a way that the modes of vibration will be only in mode 1 and mode 3, while the modes of vibration, which is mode 2 and mode 4 and so on and others, will be suppressed. So the coupling arrangement is done in such a way that the modes 2 and mode 4 will be completely suppressed, while mode 1 and mode 3 will be amplified. Not amplified, but the amplification factor will be, let's say, at 1. So now with this particular arrangement, what is happening is the input signal which is applied to this particular structure, then when the frequency matches with mode 1 frequency, the signal will be transmitted or it will be captured by the output electrode 1 and output electrode 2, and which will be fed to the electronic circuit. So when the mode frequency input signal and mode 1 frequency matches, the signal is filtered at that time. Now, whenever the input signal frequency is, let us say, at mode 2, then this particular CC beam structure will not vibrate in mode 2, means the vibration amplitude of this CC beam will be very, very less. And second thing, these signals which are captured by electrode output electrode 1 and output electrode 2 will be exactly opposite of each other. Like output electrode 1 is positive, then output electrode 2 will be negative, and therefore the combination of the output 1 and 2 will be 0. So the same thing the will be applied for mode 4 also, where the when the mode 4 suppression, mode 4 vibration will be suppressed, at the same time the output from electrode 2 now will be positive, while the output from electrode 1 will be negative, and the total output will be 0. While when I talk about mode 3 is similar to the operation of mode 1, where the mode 3 vibration of CC beam will match with the frequency, and the output at electrode 1 and 2 will be of same polarity, and it will enhance the output. So this is what we call it as a electrical coupling as well as mechanical coupling, which resonates at mode 1 and resonates at mode 3, while the operation vibrations at mode 2 and 4. Now, here I am not talking about mode 5, mode 6, mode 7. The reason is that as you go higher into the modes, mode 5, 6, 7, 8, and onwards, the vibration amplitude is very, very less, and therefore it automatically can be suppressed with this particular arrangement. Now, this particular structure, mechanical structure, was fabricated using semiconductor process at IIT Bombay, and I will talk about how we fabricated this particular structure. So here we have used a silicon wafer which is of size 2 inch, and we have used the mask plate which is of size 4 inch. Now, whenever we selected this silicon wafer for fabrication, we have used it as a single side polished. Then the orientation of the silicon was 100. It was a type N silicon, and we wanted to select the resistivity of this particular N type silicon, which is greater than 100 ohm per centimeter. So the point here is that we wanted to use a silicon material which has very high resistivity, so that the electrical currents that are going to pass through the silicon wafers will be approximately zero. Here, I have also mentioned some different materials that we have used in the fabrication. Like you can see in the table, we have a 2-inch silicon wafer. We have used SiO2 as an oxide. We have used different metals such as chromium, gold, and nickel for the fabrication of the structure. Then we have used different acids and solutions such as acetone, IPL. Then we have a photoresist remover and 5H21 acid, BHF acid. The different photoresist materials that we have used is AZ5216. You can also use SU18 and other photoresist material. So let us talk about how these devices. Now here you can see mask 1. Now this is a mask 1. We have to, I will talk about this mask 1 later on. Just look at this particular picture of mask 1, where you can see these four dots. These four dots are nothing but the basic pads for the anchors, and this is another. And then you can see this particular line which is an input electrode, and this is another two lines which are output electrodes. Then these anchors were also given some voltage, so we have given a pad for applying voltages. Here you can see three different pads were used for input signal and three different pads for output signal. So these particular pads are a ground, signal ground. We call it as a GSG pads. While this was used for only positive voltage, and ground was given into this part. So only one. So this is mask 1. Just look at this. I will talk about this in more detail later on. And then you can see mask 2 and mask 3, which were used for making the anchors. And finally, mask 4 was used for having your mechanical beams, CC beams, and the couplers. So now let us talk about the fabrication process. Now, you had been talking about from last 5 days about macro fabrications at large scales, maybe in centimeters, meters. Now let us talk about the fabrication process, which is based on micro dimensions, which is based on silicon. And here we are using semiconductor based fabrication process, which is normally adopted for electronic devices. But now we will use this process for fabrication of micro electromechanical system. So in the starting, at the first stage, what we have is a N-type silicon substrate. We have selected this N-type silicon substrate here. And on the top of, as I said, the resistivity of this N-type silicon substrate was almost greater than 1000 ohm centimeter. And we wanted this particular resistivity to be high is because we do not want any current to be passed below the N-type silicon. Now, what is happening is silicon is a semiconductor, and by adding N-type impurity into it, so it is becoming a conductor. So we want to make this conductivity of this semiconductor to be very, very less. So so therefore the resistivity, the selected resistivity of this N-type semiconductor was greater than 1000 ohm centimeter. Now to make this more resistive, we have then oxidized this silicon using wet oxidation process. So in this, when we add oxygen to the silicon, then the top of the silicon surface forms silicon dioxide. Now, this silicon dioxide is a resistive material. Therefore, the resistivity of this SiO2 is very high, and therefore it doesn't allow the passage of current to flow from the top portion of this, from the whatever structure we'll be having on the top portion to the silicon substrate. Now, once we have oxidized this now in this case, the oxidation was done for 2 micrometer. So once the oxidation is done using wet oxidation process, here I want to mention that there are two different oxidation processes. One is a dry oxidation and another is wet oxidation. So in this case, if you want to have a larger oxidation thickness, like if you want 10 micron, 20 micron thickness, then you need to go for wet oxidation process. So the time required for oxidation also reduces, and you get a higher thickness. While if you are interested in very small thickness, like 5 nanometers or 10 nanometer SiO2, then you can go for dry oxidation process. So the dry oxidation process is little bit slow, but it is used in case of thin oxidation. While for large oxidation, you can go for wet oxidation process. Now, the second step in this case was to deposit a photoresist. So here we have a lift-off photoresist, which is which can be combined with AZ5216 material, which is another photoresist. Now, this particular material was then deposited, LOR plus AZ was deposited on the top of the silicon, means silicon plus SiO2. Now I will call this as a single silicon wafer. So we have deposited this photoresist onto this silicon chip. Now once this photoresist is deposited, now as all of you know that the property of the photoresist is whenever we pass a light through this photoresist, so it becomes harden or it becomes softened. So we call it as a positive photoresist or we call it as a negative photoresist. So if it becomes harder, we call it as a positive. If it becomes softer, we call it as a negative photoresist. So now, once we deposited this LOR, now we wanted to remove the photoresist from the top of the silicon, and we have used this mask one. Now, this particular mask one, where you can see this is dark portion and this is a transparent, the white portion is a transparent portion. Now, once we pass on the infrared light through this white portion, then the photoresist on the top of the silicon becomes softened, and which can be easily removed with the help of any acid. So this particular pattern now is being formed on the top of the silicon chip, where you can see the gaps here. Right now, the photoresist has been removed, and now in the fourth step, we have deposited the combination of gold and chromium, which will now become the connecting pads and which will also form the base for the anchors. So the gold and chromium combination was used because held it can held it can sorry. So the combination of gold and chromium was used so that it can remain very well hold with the silicon chip, and it has a very low resistance. So whenever we are connecting any other electronic system, then it has a very low resistance. The connectivity is very good. Now, once this particular now this metal deposition, here we call this step as a metal deposition. Now there are different metal deposition techniques which are available, and different machines are available. All of you are more aware about all these metal deposition techniques, so I will not talk about that. Only I will see how we have deposited this using metal deposition techniques. And then in the next stage, fifth stage, is then this photoresist material. Now in the four, you can see this photoresist material in the purple color, and on the top of that we have a metal. Now now after this process is called this 3 number process is called as lithography, where we are passing the light through the mask 1, and the photoresist has been removed. Now in the step 4, when we have deposited the metal, now we want to remove this uh, photoresist material. So with the help of let us say 5:1 BHF acid, we have removed the photoresist material. And with now, when I have removed this photoresist material, the metal which was deposited on the top of the photoresist material is also removed. So now what is left out is exactly similar to what you can see in the mask 1. So now this the top of the metal layer looks like this, where it forms the connecting pads, it forms the base of the anchors. So now again the same process is now repeated, and in the sixth stage, what we do is again we deposit the same photoresist material, and also on the top of the these connecting pads. Now this, what I want to do is, now using mask 2, this particular mask 2 here, I want to make anchors for this CC and coupled beams. So now these anchors, which are of the height of nearly 2 micrometer, were then deposited in the step 7. So in the step 7, you can see with the help of mask 2, we have removed the photoresist material using lithography, and such a empty portion, such a gap is formed, where now this gap will be again filled with the help of metal. So in the step 8, what we have done is we have deposited again a metal using same metal deposition process, and we have formed the anchors for the beams. Now here again you can see that the metal is on the top of the photoresist, on the gap between the photoresist. So in the next step, which is the 9th step, where we now remove the photoresist material, and what we get is this connecting pads as well as the anchors. Now again the same process we have followed in the next stage. Now here, instead of using this photoresist AZ and LOR combination, here we have used SiO2. Now this SiO2 was used just to have another photoresist material, where now in the this stage again what we have done is we have removed the photoresist material from the top of the this SiO2 from the top of this these anchors. So once this SiO2 is removed, now we can see we have to again use a photoresist material, and then using this mask 4. Now in this you can see the mask 4 structure, where we have beams here, 1, 2, 3, 4 beams, and then we have 1, 2, 3, 4 and 5 coupling beams. So in the step 11, what we have done is we have used lithography technique, where we have removed the photoresist material from the top of the beam here, you're using acid, and we have created a gap so that we can now do metal deposition. So in the step 13 is then, in the step 13, you can see we also wanted to remove the material which is on the top of the anchors. Now, what is the problem in this case, in this step 12, is that after photoresist, what is happening is we have this SiO2 here on the top of the beam. So this SiO2 has to be removed so that we get a complete connectivity from the top of the beam to the bottom of the beam through the anchors. So using this lithography process, now we have removed the in the step 13, we have removed SiO2 from the top of the anchors. And again, now again we are going back to the similar process of depositing uh, LOR, and then following with the step number 15, again, let's go back to the mask 4, where you can see the structure similar to the coupled beams as well as CC beams. So now, after removing the photoresist using lithography technique, you can get this kind of structure, and then again we have a metal deposition process here. So now once the metal is deposited on the step 16, and then finally what we get is step 17, which you can see like that. So in the last stage, in the last two stages, what we have to do is to remove this photoresist using acid. And once the photoresist is removed from the top of the SiO2, which is here shown in green color, now you can see here you are exactly getting the structure that is a combination of all these. So this is similar to this kind of structure you can see in the block diagram. So we are getting this kind of structure actually fabricated. So you can see here these beams are made up of metals, while and these connecting electrodes, input electrodes and output electrodes, which are of metal, which are there now fabricated, built on the top of the silicon chip. Now in the last stage, what we have is to remove this green color SiO2 using any acid, which we have used 5:1 BHF. Now once you remove this acid, then finally you get the final structure which I have shown in the block diagram. So finally in the step 19, you can see the structure has been fabricated on the top of the silicon. So here I will show you, this is a fabricated device which I have done at IIT Bombay. And from this you can see, this is actual ACM image of the fabricated device. And here on this side, you can see the coupled beams. Below that, you can see the input electrodes and output electrodes. Here we have done measurements, and the gap between the CC beam and the bottom electrode was measured to be 387 nanometer, which is approximately 0.3. Okay. So this particular structure we have fabricated, and this is an ACM image that was obtained at IIT Bombay. And this particular fabrication, we got it after 3 iterations and almost it took us to 6 to 7 months to finally get this. So we had different problems how regarding fabrication, which we will talk about someday later on. So now let us see the physical parameters that we have got in this case. In the beam plane, we have designed for 76 micrometer. We got 76 micrometer. The beam width was designed for 6 micrometer. We got 8 micrometer. The thickness, desired thickness was 0.5 micrometer. We got 0.513 micrometer. The resonator gap was designed for 0.36 micrometer. The what we got is 3.387 micrometer. The coupling length beam was 10 micrometer, right? The width was 6, which we got 8 micrometer after measurement, actual measurement and design values. The young modulus, density, Poisson's ratio, etc. We have measured here. And finally, the transduction area, that is the area which is overlapped between the beams and the input and output electrode, which was measured to be 640 micrometer square. So after these mechanical parameters, physical parameters that were measured, the electrical parameter was the static capacitance, the applied DC voltage. The current that we have measured was only 0.5 picoampere, and the resonant frequency, because of the change in the physical parameters, the length was 76 micrometer, but the width of the coupling beam and the width of the width of the CC beam after fabrication has been changed to 8 micrometer. So the designed value for resonant frequency mode 1 was 440 kilohertz, which we measured was 400 kilohertz. It was designed for a bandwidth of 4.4 kilohertz, but we got 3 kilohertz. In the mode 3, the designed value was 2.4 and the measured value was 2.5 megahertz with a bandwidth of 24 and 20 kilohertz respectively. Output power and transmission loss, these electrical parameters has been given in this given in the table, right? So this is the result of when we applied mode 1 frequency at 400 kilohertz. So we got this response, which was the almost minus 20 dB, and the Q which is measured was 133 in air and not in the vacuum. So, and as you can see here, the mode frequency, vibration mode 2 and 4, as well as any spurious modes were also suppressed in this case. You can see the waveform, the signal waveform for mode 3, where at 2.5 megahertz with a bandwidth of 20 kilohertz and with a Q of 129 in air and not in vacuum. While again you can see here in at this particular frequency as well, the mode 2 and mode 4 as well as spurious modes frequencies were एक 5-10 मिनट. Okay.
चालेल 5 मिनिट वगैरे.
Okay. So was suppressed.
दुसरे स्पीकर ऑलरेडी जॉईन झाले.
Okay, ठीक आहे. 5 minutes. So now the same measurement was also done at different temperatures, and we wanted to find out the frequency shift versus temperature. And you can see here we have taken these frequency measurements from minus 10 degree to 100 degree Celsius, and what we got is a good for this particular mode 1 and as well as in the mode 3. So finally, in conclusion, is that the MEMS dual band. So we have two different bands at mode 1 and mode 3 was designed, fabricated using electrical and mechanical coupling scheme with 2-port electrical configuration and sub-micrometer transduction gap. So the gap that I told you was 0.3 was a transduction gap. So these are the results that we got at 400 kilohertz, and then 2.57 kilo megahertz frequency. The thermal stability was at 445 ppm and 510 ppm respectively at mode 1 and mode 3. And then these are all the different measurements that we have done. And finally, we concluded that this particular system, this particular arrangement of electrical and mechanical coupling scheme can be used in case of multi-band filters in wireless communication system. So with this, I want to stop here. And if any of the participants have any questions, they can please ask me.
अनम्यूट कर निखिल सगळे अनम्यूट आहेत. Okay, participants, you can unmute yourself and you can ask the question.
चॅट बॉक्स मध्ये काय टाकलं?
Chat box दिसत नाहीये. Which lithography tech is better to use?
Which lithography means, can you please specify?
Pratima madam.
Yes, sir. Actually, there are a number of different techs by which we can do the lithography, or means we can remove that particular unwanted material, sir. So it would be better to use in a very precise manner.
So
Means,
stereolithography is when we talk about semiconductor, we have a stereolithography there.
Ma'am, are you satisfied with this?
Yes, sir. And another one thing is means once you are dealing with the that particular miniaturized synthesis or fabrication of the devices, then
Yes.
what are the basic problems through which problems we have to face while depositing or fabricating all these things? Rather, we have to deal with the silicon, but
See,
whatever it is.
yeah, so here silicon is just a substrate. It's just a, you can see it's just a platform where you are building your any design. So you can use glass or any other material also. Okay, only the issue is that the particular material should be compatible with the entire process. That's one reason. The second point that you are talking about uh, uh, is a yeah. Can you please repeat? I just forgot it.
Yes,
The
sir.
issue, yes, yes. So you were talking about the challenges while fabrication. So mostly the challenge is that the first and very important thing is the entire process that you are going to fabricate. That particular process should not be of more than 3-4 lithography steps. Now here, what happened is we had 3-4 lithography steps. So the alignment of the mask. So let's say when you have a first step lithography, then you are moving to the second stage, then you are moving to the third stage. So all these different masks has to be properly aligned in different situations, different processes. So alignment is a bigger issue then, and it's more of a skilled job. The operator has to see that how you are aligning this mask. So different alignment like symbols has to be created on the mask so that that is one thing. Then second particular challenges that we have is the making of the mask also. So whenever you are making the mask, if there are varied dimensions, like let's say you are 2 micrometer and then suddenly you are going to 200 micrometer and then you are going to 500 micrometer. So this particular so you have to see that you gradually move from 2 micrometer to 100 or 200 or 500 micrometers. Then the third thing is that whenever you are fabricating, you need to see every time that your process is completed, means whether it is error free or not. So once you done first stage of lithography or first stage of, let us say, deposition, you need to see under microscope, you need to do thickness measurement, length measurement, thickness measurement, or width measurement. So these measurements has to be carried out periodically, so that your entire fabrication is done. So these are some of the challenges which are involved while fabrication.
Thank you, sir. There are many more questions, but later on I will put a timely. Thank you. Thank you very much, sir.
Thank you, ma'am. Uh, Dear participants, on behalf of participant, because now I'm become a part of you, on behalf of college and you, I thank Dr. Morankar sir for sharing their work with us, which is electronic based work. Many of their participants, they are from electronics background. So I think this lecture must have been useful for them as well, because material is such a kind of thing that it don't have any kind of boundaries. Every department, they require a material. Rather, I say uh, improvement of every technology and department is at the root. It is material only.
So it's a combination of electronics and mechanical.
Mechanically, yes.
So
yes,
maybe
nowadays.
like you have robotics branch which talks about combination of electronics and mechanical at macro level. Maybe sometime we will have a micro level combination of mechanical and electrical, which we'll call it as a MEM system.
MEM system, yes. So thank you, sir. Thank you for
Thank you.
joining us.
Thank you very much for inviting me for this lecture. And thank you all of you for participants for patiently listening to me. Thank you very much.
Thank you, sir. Amal, sir. Uh, Dear participants, just a minute.